Hi and welcome to this first video on normal distributions, and this is the second part of Unit 4 Topic 4, which I'm splitting up away from that probability density function work. Normal distribution is a particular example of a probability density function. So probability density functions for continuous random variables represent any type. A normal distribution is a particular example, which we're going to go through now, and this is a large chunk of this topic. So there's your learning goals success criteria. You can pause now to have a look. We of course are using the Cambridge text, and they are the chapter references with the suggested questions from us. So let's talk about normal distributions. Sometimes when you have a large sample, you might say that this can be represented as a bell curve. So you've probably heard the word bell curve before. So here's some data. I actually randomly generated some data. The heights of 10, 50, 100 and 500 bean plants. And I've represented this into a frequency histogram, which I've converted into a probability histogram. You can tell it's probability based because here are my probabilities. So this probability histogram represents a large set of data. Now you can see here in the first one with 10 bean plants, there really is no discernible pattern. We seem to have a bit of a clump down the bottom end, which might mean something, but otherwise not much in the way of a pattern. This, on the other hand, kind of starts to peak in the middle, 50 bean plants. Now we're starting to get a real pattern. There's a drop off there I'm concerned about, but that could just be an anomaly in the data. Again, 500, we've got that nice pattern there. And this is generally called the bell curve. It looks a little bit like that. If a data set is large enough and a suitable variable, so it has to be a particular type of variable, which we'll talk about a little bit later, then it should model towards this normal distribution. There's today's joke, a paranormal distribution. But seriously, the big picture is this. A normal distribution should look like that. It's a bell curve. Now, it doesn't end. Looks like it ends. It doesn't end. It goes on infinitely. What that means is, technically speaking, if a set of data represents a normal distribution and it's continuous data, so let's say it's the height of bean plants, as I spoke about earlier. You grow a bean plant for 3 weeks and we measure the heights of all the 3-week-old bean plants. And let's say they all say on average about 10 centimeters tall, and they're spread out, standard deviation of 2 centimeters. One of those bean plants could be a meter tall. It's unlikely. It's really unlikely. It's way up here. It's so close to zero it's not even funny. But it is still possible. And in context, in life, you might say that's potentially possible. Most contexts, though, will have some sort of restricting feature. At some point you go, yeah, no, that's unrealistic now. But the theory here goes on to infinity in both directions. So what we do have, though, is the center of our data. We call that mu, which is our mean. Now, mu is also equivalent to the expected value of a set of data, which we've already spoken about. And it's sometimes written as x bar as well, but we'll be using mu. And then we have some data. But most of our data is here in the center. Some of the data is here, and it's just a little bit out in the wings, but not very much. Any continuous set of data that is not contextually skewed or that has 2 defined peaks. So what I mean by that is you might do a gender-based data collection. You might find there is actually a difference, just based purely on biology, between the results for girls and boys that creates a 2-peak function, which is not going to naturally be a bell curve. Again, though, if we have a large enough set of data, there might be a predictable feature in it, but for this purposes and for this topic, it doesn't make sense. So for any continuous set of data that's not contextually skewed or has 2 defined peaks or more defined peaks, it can be said to be normally distributed. It is never exact, but we can use the properties of a normal distribution to make a reasonable guess. And this is, of course, for continuous data only. So let's talk about the standard normal distribution. A normal distribution is described by a center and spread. So I've got 3 of them drawn here, one in black, one in purple, and one in orange, which I'll talk about in a second. The standard normal distribution has a mean of 0 and a standard deviation of 1. So that sigma is our standard deviation. That's the standard normal distribution. And they're called z-scores, which I'll point out to you a little bit later. So we'll talk about z-scores again in a second. So our black one is our standard normal distribution. you can see that it's centered here at 0, and it's got this spread of 1. The spread's really hard to consider visually what that actually means, but it's a really good comparative tool. So let's have a look at the purple one. The purple one has a mean of 2, so there's our center at 2, and it's got a spread of 0.5, which means that because it's got a smaller spread, it's more compact. And if we make this graph more compact, but the area under the graph still must be 1 because it's a probability density function, it pushes the peak up. That's why we have a higher peak. So compacting it, i.e. decreasing the standard deviation, will increase the peak in our normal distribution here. But it is still a normal distribution, it's just not the standard normal distribution. This orange one has a mu of -1, that's possible, depending on the context. Standard deviation is now 2, so that's spread it out, which therefore in turn flattens that peak down. Now again, I've not set any factor. It doesn't necessarily flatten it down by a half or double the height for the standard deviation of 0.5, but you will see that discernible visual difference. So hopefully you can see how we can translate different normal distributions to create different shapes and different graphs to represent our situation. This is the probability function. Now, unfortunately, it's a bit complex, but you don't need to know too much about it. It may come up. So the distribution function is, and we don't have a second one, there's no 0 otherwise, this is from -infinity to infinity, inclusive. So f of x is 1 over the square root of 2 pi e to the -½ x squared. And so the integral between infinity and infinity is equal to 1 because probability density functions have an area below of 1. But there's an x squared inside an exponential. This is beyond the integration needs of math methods. So if you were asked to find the area under a normal distribution, so you might be asked to find, for example, the area under this normal distribution between, say, 1/2 and 1.5, which would be this area, and as a probability, and you needed to use this method, it's not the only method, but you were going to use this method, you would put 1.5 here, 0.5 there, and we would expect you to use your calculator. We don't expect you to be able to integrate this particular function. So just keep that in mind. Let's have a look at an example, and I'll show you how to use the calculator. Determine the probability that x is between -1 and 1, where x is the standard normal distribution. So we go to our calculator here. We go, of course, to Math. F6 gives us our integral function, and now this is the fun. So you'll probably get used to this function. It's 1 over the square root, and I've just done the xth root, the square root of 2 pi, which is above the times 10 to the power of x, and then it's times e to the power of, and we've got another fraction inside here, half x squared dx, and of course that is going to be, in this case, between -1 and 1. Well, here's my video gaff. I'm just going back. I've just cut out some of this, but you'll notice here that I have made a mistake. Pause now and see if you can spot the mistake because I got the wrong area. Okay, and if you didn't spot the mistake, of course I've forgotten the negative in front of here, and I was a little bit confused for a moment there. Execute 0.68269, and that is what I was expecting. So from my calculator, the probability -1 is less than or equal to x is less than or equal to 1 is equal to 0.682927 or 269. 269. It's probability. We try and keep it as accurate as we can without going too far. 4 decimal places is often quite good. So that's example 1. All the best.